Hi, I'm Mike Balfour. I'm a senior software engineer at Amazon. This talk is about modularity in the Open3D engine and the approaches that we took to designing terrain as a modular system. I'm going to start by introducing you to the overall design challenge that we faced, dive deep into what it means to build modular systems, and then finally, I'll show off the fruits of our labors. So first, some background. I've worked on AAA games for over 20 years, from mobile to console to PC, in a variety of genres. For the past 5 years, I've been working on O3DE with a specific focus on building virtual worlds of arbitrary size and fidelity. I've always loved nature, so it's been a real treat for me to get to work on world building systems in O3DE. And that takes us to the challenge. The challenge that we faced is that the Open3D engine is a modular 3D engine at its core, and it was missing a terrain system. So we took on this challenge of designing and building a terrain system that's performant, scalable, dynamic, and modular. It's been a journey, and I'm going to walk you through our approaches to it. But first, I should explain what a terrain system even is. A terrain system is a system that defines the geometry, color, and surface types for a ground surface. The system includes all of the data management, authoring workflows, rendering, and physics that's needed to produce a virtual terrain. To put all of this in context, here's a quick look at a virtual terrain that I authored for this talk. This terrain is 4 kilometers by 4 kilometers in size, and I've decorated it with 2 airstrips and a little bit of sparse vegetation. I'm going to be using this terrain throughout the talk to help illustrate some of the terrain design concepts as I go along. So, what does it mean to be modular? When building a system, you can either choose to build an integrated design that does exactly everything you need, kind of no more, no less, or a modular design where you divide your needs into smaller parts that can be combined into the result that you want. For example, a Lego minifig is an example of integrated design. Even though it's made out of pieces, everything from the hair to the outfit is typically very specialized and designed to produce one specific character. A Reese's Pieces Big Cup is also specialized. It's a specific combination of chocolate filled with peanut butter, filled with candies containing chocolate that contain more peanut butter. On the other end of the spectrum, for modular design, you've got a pile of generically shaped Lego pieces or a set of just raw ingredients for cooking. You can combine these in endless ways to produce any number of outcomes. It's a little more difficult to get to the exact thing that you want, but you have a lot more variety and choices along the way. In applying modularity to terrain, there's 2 different types of modular design that we wanted to achieve: system modularity and content modularity. System modularity is the ability to make pieces of the system itself optional, reusable, and replaceable. Content modularity is about building a system that lets people author content that's composed of optional, reusable, and replaceable pieces. So let's start by talking about how to make the system itself modular. With system modularity, the goals all really come down to creating optional and replaceable system pieces. We'll dive into each aspect of this a little more closely. At the highest level, there's making the entire system optional. Not every project needs terrain. At the highest level, a modular terrain system should mean that the entire system is completely optional. If people don't want to use it, it shouldn't exist or consume resources. The solution to this in O3DE is gems. Gems are packages that contain combinations of assets, code, and system dependencies. Gems can be easily distributed and shared across projects. And because gems are optional additions to a project, they provide an easy way to enable and disable a system at the project level. If a gem isn't included in a project, it's not even compiled, and its assets won't be used. So we could have built the entire terrain system as one single gem, but we spent some time considering the level of granularity that we wanted. And this tends to be a recurring theme in modular design, finding that amount of modularity that fits the best. When looking at this, we were considering whether or not any functionality would be reusable on its own, and whether any implementations should be completely replaceable and swappable through other gems. If so, then these are good candidates for splitting out. But on the flip side, dividing up into more gems can lead to longer build times and load times. They can also cause testing challenges. When you have systems that rely on other systems, you can either create integrated tests to test all of them together, or you can mock out systems to test each one in isolation. Fortunately, O3DE has mechanisms in place that make it easy to do both. So with terrain and vegetation, we landed on a division of 6 separate gems. At the base, we have surfaces, gradients, and noise that provide general concepts that can be used on their own. In fact, gradients have already been used with other rendering features, and noise functions have been used with the navigation system. The terrain and vegetation systems sit on top of these 3, but each fully contain their individual systems while relying on these base gems. And then at the very top, we've got Landscape Canvas, which is an optional node graph editor that can be used with vegetation and hopefully sometime soon with terrain. We chose these separations of these 6 systems carefully based on the combination of what functionality seemed useful in isolation and also what reduced the amount of dependencies between systems. For example, both terrain and vegetation use gradients and can eventually be used within Landscape Canvas together, but there's no dependencies between them. Terrain and vegetation can be used completely separately from each other. These loose couplings between systems represent another key goal towards making our system modular. The fewer dependencies that we have, the easier it is to keep systems optional and replaceable. And this really leads to the notion of interchangeable parts at a system level. It's what allows us to say, I depend on the generic concept of physics instead of I specifically depend on the physx physics library. Loose coupling is really a common engineering problem, and it's typically solved through good interface design. O3DE provides multiple ways to define interfaces and event communication to keep a clean separation between systems: AZ interface, AZ event, and eBus. Each one of these different methods has a different set of strengths, but the set of them together provide a robust tool set for separating systems. There were a few big considerations that we needed to think about when designing the terrain interfaces. To build out the interfaces and events for the terrain system, we ultimately chose to use the eBus or event bus system because it gave us the concurrency support that we needed to build out a highly threaded system. So the next question that we faced was where to define the interfaces. Because these are meant to be a generic promise of functionality, the definitions can either go in the engine itself, if they seem core to what a 3D engine supports, or in a separate gem that just defines optional interfaces, or into the gem of the system you're designing if the interfaces are specific to that system. Terrain is pretty core to a 3D engine, so we chose to put the interfaces in the engine even though none of the implementation is there. By doing this, we're defining what the engine expects out of a terrain system without requiring any one specific implementation. One other thing to consider when designing interfaces is that it's helpful to make a clear distinction between requests that feed into the system and notifications that are sent out of the system. The terrain system processes requests and then sends out notifications. Other systems can then process those notifications and send out requests. As an example of how this plays out, we wanted our terrain to support physics. O3DE currently only has an optional physx implementation, but someday it might also support Bullet, Havoc, Jolt, or any other physics library, so we don't want to get tied to a specific implementation. On the flip side, we also want physx to be able to support terrain without depending on our specific terrain system or even requiring terrain to exist. The solution to this was to define generic eBus requests and notifications for height fields, which each system then uses. With this separation, the terrain system can work equally well with any physics system that supports height fields, and physx can work with any height field authoring system, whether it's terrain, external tools, 3D meshes, or procedural generation. We've gained a lot of decoupling and flexibility on both sides just by inserting a well-defined interface in between. So we've talked about making the entire system optional and swappable, But now let's look at doing that at a finer granularity within the system. This is where we really get to designing our individual building blocks. Not every level or project has the same set of requirements, and even within a requirement, there can be different implementations that fit the needs better or worse. And the solution to this in O3DE is components. O3DE uses a component entity system for building out worlds. Entities are unique in-game objects, and components are modular pieces of functionality that can be added to each entity in the world. Components can be fully distinct, but they can also interact with other components and reference other entities. Because components are added to entities, they're the perfect building blocks for building up that set of functionality that's needed on an entity. Components have a concept of provided services and required services, so it's possible to create different interchangeable components by having them provide the same service, even if it's in different ways. These components can then all be swapped out at authoring time without needing to modify anything about the existing terrain system. New components could even be implemented in different gems. For terrain, we chose to divide the components up between conceptual data, rendering data, and physics data. And this is admittedly a lot of components just to create one section of terrain. By dividing up the functionality this much, we've made it a little bit harder to author initially, since there's more clicks needed to add all the separate components. But the payoff is that it gives us a tremendous amount of power and modularity. Each of these components now becomes an optional piece of functionality, which lets us tune each section of terrain to use only the features that it needs. Also, each component becomes an independent touch point that we can swap out for alternate functionality. For example, the terrain uses a macro color component to color the terrain, but it's possible to create different implementations of that. The one that we provide directly uses an authored color texture, but another one could be created that uses Mapbox or some other service to fetch satellite data and use that for the color. A third implementation could use gradients and color ramps and procedurally generate the color instead. All of these just need to meet the promise of providing color somehow, and then they become swappable. Other components can be attached to the level itself. In O3DE, a level is a playable section of a project that generally represents a self-contained simulated world. For terrain, we made the system optional for an entire project by putting it in a gem, but within a project, level components provide a way to turn a system on or off for an individual level and to set tuning parameters that are specific for that level. For terrain, we chose to create 3 different level components, which allows us to keep the base system separate from the renderer and from the debugging features. This lets us enable and disable terrain rendering and debugging separately from the system itself, and even makes it possible to swap in different terrain rendering implementations over time. One of the biggest debates with our component design is the choice of the level of granularity. We could combine multiple components together and make a single catch-all terrain component that provides all the features on one single component. And actually, anyone could build this themselves if they wanted by combining our current components together. But for each use case that's solved with an integrated design, there's another one that's better suited to separated functionality. Another consideration is how the component behaves in the editor versus the runtime. For us, we've taken the approach of having the runtime component active in the editor, which gives us a single dynamic system that updates equally well in the editor and at runtime. This means that we can change the terrain dynamically as the game is playing or as the project is running. If we were willing to accept a static runtime system and didn't want the terrain to be changeable, we could have split the components into separate editor versus runtime components and had an even more performant runtime, but at the cost of not being able to change it. A third consideration is in how to set up dependencies between related components and the entities that they rely on. Component dependencies can be used to control initialization order between components, but entity dependencies don't have this guaranteed initialization order. In our terrain design, updating dynamically at runtime becomes not just a feature, but a requirement, because the entities that provide data can start up in any order, So we had to design it to listen for change messages and not just rely on strict startup ordering. For this reason, modular components can be more difficult to build, but a little extra pain upfront in development really brings payoffs and flexibility for our content creators. So now let's take a look at what it means to design for modular content. When designing for modular content, we're basically trying to make the content easy to author, easy to lay out spatially, and easy to modify it across time. So let's take a look at each of these. The single best building block that we have for modular content in O3DE is the prefab. Prefabs are a collection of entities that can be instanced and reused, and the collection can even be dynamically loaded and unloaded at runtime. For this presentation, in the level that I was building, I built my airstrip as a prefab. It contains over a dozen entities defining the jet, the hangars, and then some terrain modifiers that flatten the terrain and add the concrete terrain surfaces for the runways. By building it as a prefab, I was able to place multiple copies of this airstrip around my world just by instantiating more prefab instances. I could even load and unload each airstrip dynamically at runtime if I really wanted to. So for the most part, you can put anything into a prefab, but when working on the terrain system, we found a few tricky things that you need to consider. First is that the entities in the prefab can't currently reference any entities outside of the prefab. And this works great if you've got self-contained data that you're adding to the world. It's a little bit problematic with the terrain system though, and it required a bit of creativity to work around because with terrain, we're generally trying to overlay or modify existing data and not just replace it wholesale. There's some features planned for prefabs that'll solve this problem, but for now it's just something to be aware of when you're designing. Second, as I mentioned before, the timing of initialization can make things a bit tricky because entities can initialize in any order. If your systems rely on different entities to provide different data, you're going to need to have some system of change notifications to react to it. And this also comes into play with refreshing. If you have a system that's using newly loaded content to modify existing data, it's important to notify the system to refresh itself correctly on loads and unloads. When designing a system that has modular content, another goal is to divide the content itself up by function. Different types of content are often produced from different tools, so this separation often naturally occurs, but I found that making a conscious choice to design around this usually leads to other emergent benefits over time. For the terrain system, we chose to separate height data, macro colors, surface types, and materials. So let's take a look at what that looks like in practice. Here's what it looks like to modify height in isolation without modifying the color or the types of surfaces. And this is isolated color modifications without modifying the heights or the surfaces. And this is isolated surface modifications without modifying the height or the color. So it's very flexible, but it might seem a little questionable. When would you modify height without modifying color and surface types too? Why would you do that? In simple levels, you probably won't. Generally, your data will match 1-to-1. But in complex levels, you can start to play with that flexibility. For example, you could dynamically spawn craters or robot tracks that only modify the heights. Or you could swap out just the surface types and colors after a large forest fire while leaving the shape of the terrain intact. For flight simulators, you could choose just to not even load any of the surface detail data at all, except for when you're near the ground at takeoff and landing. Another very related goal is the concept of mapping data to regions in the world. At a minimum, this provides an easy way to do tile-based authoring and streaming by letting people author separate regions of the world at the same time, letting multiple people work in parallel, and also supporting streaming by being able to have regions that you can load in and out dynamically. But one of the trickiest pieces that we've run into when building systems that operate based on world regions is what to do when they overlap. You need some method to decide which data wins. So far, our solution for both terrain and vegetation has been to use priority fields on our data, so that way you can specifically say which one takes precedence. But even with that, if you have overlapping regions of the same priority, the results still become non-deterministic. The other surprisingly tricky piece is how to handle edges. When working with box regions, it becomes unclear what should happen when two adjacent regions share an edge. In our design, we've chosen to go with a pattern of minimum side is included and the maximum side of the box is excluded. So that way there's always one clear owner of each edge. But this is definitely an area where it gets a little confusing and non-intuitive. The last goal of our modular systems is to enable them to be scriptable. Beyond just loading and unloading at runtime, we also like to be able to dynamically modify the systems. In O3DE, we can do this through the behavior context. It's a way for systems to expose their data and functionality outwards to scripting systems. This enables users to combine systems together in unique ways at runtime without having to modify the core engine to get their specific behaviors. As an example, the little script at the top is dynamically modifying all of the terrain in our level. I didn't even honestly know this was possible to do it at this scope until putting this presentation together, but this is the power that comes from building a dynamic system and exposing it to scripting. Now, I'm not saying anybody would want to modify their terrain this way, but this is an example of things we didn't even have to build functionality for, and it still just works. The biggest challenge with using the behavior context, though, is that it's used by script canvas, Python, Lua, and anything else in the future that wants to hook into it. One of the things we learned while working on terrain is that if you design an API or a method that works well from one system like script canvas, it can often mean that it's harder to use it from another system like Lua. And so what we've found through trial and error when tackling this is that really you just need to make your APIs as simple as possible, because the easier they are to use, the easier it is to use them across any scripting interface. So finally, let's just take a quick look at how all of this plays out in practice in the terrain system. So this is a look at the terrain system in action in O3DE as an example of the power of modular systems. And this video was captured while I was assembling the sample level for this presentation. And it's all built using the current O3DE development branch. You can see from watching this just how quickly it is to assemble terrain, modify it, and get it laid out. Here I'm instantiating the airstrip prefab, and you can see how we can interactively move it to different places in our level and dynamically affect the terrain as we're placing it. And then even within that, the terrain surfaces themselves can be dynamically modified just by adjusting these shapes that say where the terrain surface goes, or we can adjust the blending between different materials. And it's all very interactive and reactive. And anything like this that we can do in the editor, we can also do in the runtime. So this is showing the final level that I built at runtime, doing a bit of dynamic modification to time of day and the terrain surfaces themselves, and then a flyover of the level just so that we can see the entire level from above and then up close at the end. And so you can see we've got the performance tuned here, so that way we can have pretty far draw distances for this 4-kilometer terrain, all the way down to some really nice surface details when you get up close and personal with it. So, in summary, it can be more difficult to design for modularity. It takes more thought and care in the design, and it takes longer to build, but at the end, it provides immense payoff and flexibility. O3DE as an engine gives us a lot of different tools to make modular design easier. Gems, components, interfaces, events, and the behavior context. By using all of these tools, we were able to build a terrain system that achieved both system modularity and content modularity. Finally, these are just some helpful links. The Houdini terrain tutorial is the one that I followed to author the terrain that you've seen here. I was able to build it from scratch in just a few hours. And there are also a lot of great websites for free PBR materials and 3D models. These are the attributions for the specific free models and materials that I used in this level. So if you've got any questions, you can find me on the O3DE Discord server as Mike B. Amazon. Thanks for your time.